Okay, so last week, like I said, we set up the FEA. So now we're going to go and we actually get our loads, our pressure loads from CFD. So previous work, we used CFX, which is a bit easier to use than Fluent. So I just stuck with that for now. So we already imported the geometry. We go to mesh. It'll take a second to load. Also, disclaimer, this is no be all and end all of CFD. This is just kind of the work that's been going on for the fins. I want to make sure other people learn how to do it and learn how to improve it and stuff. Oh, opened in the wrong window. Okay. Hopefully you guys can see this model now. So it imports all the solid fin model and the fluid domain. So we basically need to suppress everything except the fluid domain. Unfortunately, we lost all the names of stuff, so I'm just gonna have to click through and find, or either click on that, and then you can go suppress all other bodies. So here's our fluid domain. It's this rectangle, which basically has this mold pretty much of the fuselage and fin. You can see it's like cut out. And basically in CFD, you model the fluid domain. So FEA is the actual solids, and then CFD will do the fluids. So we have our geometry. There are no connections or anything. Just start by generating mesh. And we're all on the student licenses here, so I don't really know how well we can get the mesh. But the finer the mesh, the more accurate usually. This is what it generates as a default. That's not bad, I don't think. It's pretty small, close to the fin. But you can insert various methods. Just apply the hex element, I think usually works pretty well. I won't spend too much time on the mesh because it sucks when you get to the end and then you realize you have too many nodes and you have to resize everything. Hopefully this loads. Oh, the mesh, by the way, if you don't know, is basically each one of these is a little, okay, I did not like that method, so I'm just gonna delete that and remesh. Basically, each one of these little cells, they kind of do a little calculation of like fluid flow. Same thing with FEA, each little mesh does a little like stress calculation, so it numerically solves the problem. Try sizing. I just make the fuselage maybe a little bit smaller. There's no kind of hard and fast rule on this, but there's lots of ANSYS meshing tutorials that you can look at, and then it makes everything a little bit smaller. We'll just stick with, this is basically a default mesh. And so also in your meshing, you also have to add your domain name. So basically this edge that I made is the like aft of the fuselage. So the flow is going to come in this way. So this, and click on that face, right click, create name selection. And this is an inlet. You can name them actually however you want, but if you name them like inlet, outlet, stuff like that, the software will recognize what it is. And it's just a little bit easier. So then the opposite side is the outlet where the flow is coming out. Okay, so now we have, this guy is the fuselage. Hopefully you can tell. We'll right click, create name selection, call this fuselage. And now we have to select all the fin walls here. So a good way to do this, you can change your selection mode to box select. And then if you just like drag a box, it will select everything in that box. So now that's the whole fin. Create name selection, fin. So those are both walls, but Simon was saying you should separate those. I'm not 100% sure why. I'm not sure. Yeah. So then your remaining stuff, I change that to your single select. Are these kind of walls open to the free air? So control click, you can select multiple. So then all the sides and then the bottom face, including this guy, because this is not actually part of the fuselage. This will be like free stream. Select all those. So sides and the whole bottom. Create name selection. And we'll just call this free stream. Okay. Now we have all our name selections, inlet, outlet, fuselage, fin, free stream. So basically you label all the faces that are kind of the boundaries of your fluid domain. So save. And that's all you need to do in the meshing, except maybe improve the mesh. Close that. Sometimes the mesh does not like to generate. So if there's a lightning bolt, basically it means you need to update or generate something. So right click, update the mesh. Okay, setup. So double click on setup. If you have any questions, just feel free to let me know, or we kind of get going on the actual setup. Okay, so now it opens up this CFD pre thing. So this is the CFX kind of interface. The other two steps are the same in CFX and Fluent. So first thing we want to do is it will default to subsonic flow, but we want to change it. So if you right click on default domain and hit edit. So here are your basic settings. It's a fluid domain. You don't need to change any of these locations. The material for supersonic flow. So this is actually this is actually supersonic flow, even though it's a 10K rocket. It is about Mach 1.2 max speed. So change to air as ideal gas. Basically, there are all these relations for like Mach number and supersonic flow that assumes air is an ideal gas. So if you use that assumption, you can use the supersonic models. And then the basic settings, fluid models. This is total energy. And then these are all stay the same. This basically says there's no combustion, no radiation. And then that's all you have to do. Hit apply. Okay. So now you have to tell the solver what all your boundary conditions are. so that they know how the flow is going to behave. So right click, insert boundary. And so we'll start with the inlet. So if you call this inlet, it automatically selects that it's a inlet boundary type. And then on boundary details option, so we are supersonic. We're basically mimicking the conditions at max Q. Yeah, normal speed and pressure. Relative static pressure is 0. That's just, yeah, telling us working like gauge pressure. Normal speed, so the speed is Mach, I think 1.2, so it's about 410 meters per second, I believe. And it seems like before we were changing the turbulence to high intensity. I assume it's because supersonic, there's going to be a lot more turbulence. And static temperature, so the temperature at whenever this is happening, it's about 2,000 feet altitude, so it's about 11 degrees Celsius. So make sure you change it to Celsius, not Kelvin's the default. And then apply. So now it's showing our inlet. Click insert boundary. So now we'll go do the outlet. The outlets by default are just a pressure outlet, so boundary type outlet. You don't need to change anything. Supersonic. You don't need to change anything. The boundary condition in actuality tells you there's like 0. The pressure here is just the relative static pressure, so it's basically saying there should be no disturbances over here, I believe. Oh, I should mention for this model, the kind of rule of thumb is to make it at least, you can fit 3 kind of fins. So that's about how long it is. You have space, you have your fin in the middle and then space for 1 more fin on either side. It's kind of hard to, so this domain might not be big enough. Maybe we want to consider making it bigger, but it's kind of hard to size without running the simulation once. Insert boundary. I'm going to call this free stream. So automatic sets free stream for you, and then the type is opening. Boundary details. So opening, pressure, and direction. 0 relative pressure basically means that when you cross this boundary, there should be no pressure difference. And that's because hopefully you're far enough away from this object that there's no pressure differential and you're just at atmospheric pressure. And high intensity turbulence again, and the temperature is the same, 11 degrees Celsius. So we still have 2 more boundaries, and that is our fin. So anytime you have a solid, your boundary is between like the solid and fluid domain, you have a wall. And basically it's a no slip wall. So basically the flow does not slip along the wall. And so I think Nick did some research and said that the sand grain roughness is about 32 microns, sorry, 3.2 microns, I think. Also, I might have messed up some of these settings along the way. I'm kind of doing this off memory, but this is the gist of it. Adiabatic heat transfer is fine. And then the fuselage has the same boundary condition. Boundary type, wall, details, no slip wall, rough wall, 2.2 micron. Okay. So now you have told the computer what all your boundary conditions are. Now the beauty of CFX is now you can just solve it, whereas Fluent, there's a couple more things you have to do. So we'll just save. And if you open up solution, okay, I'll just move these up here. So usually run double precision on CFD programs. I'm not 100% sure why this, but it seems like everybody always does that. Start run. And it will, okay, there we go. So now this is it crunching numbers. This graph, it will load in a second. So these colors or these lines are basically the residuals. Residual in any kind of finite element method, which includes like structural FEA or CFD, is like the kind of error between the estimated solution and the actual solution. So you can see at the beginning there, 1 times 10 to the negative 2. And it will keep crunching and they'll keep going down. And eventually, hopefully you get, I think to the negative 6 is ideal, but seems like below 10 to the negative 3 is still pretty good too. So this will load. I think this took about 15 minutes when I ran this the other day. So this might take a little bit. So I'll just stop the recording or pause the recording. Okay, so that will run for a while. This took 20 minutes, I guess. Now press OK. I'll save so don't lose anything. So now, if you want, you can get results. We're not, well, I mean, we are concerned with the CFD results, that they're actually accurate, but that's not really what we're looking for. You can, oh, I forget how to do this. Oh, so you can like insert contour. So this will insert a pressure contour. So there's the pressure plot, which is basically what we're after. So yeah, looking at sinking these bolts actually into the foot, because you can see creating like this really weird high pressure, like low pressure kind of thing. But typically you have like high pressure at the front of the fin, which we see the yellowish red here. And then at the back of the fin, you get like the low pressure, negative pressure region. And you can do other stuff. Streamlines. So you can see the streamlines and stuff. Just kind of fun stuff. It's not super consequential. So now this problem is fixed because it sees there's results. So now we can go into our FEA. So we set this up before, but if you, typically you do your CFD first and then set up your FEA, but it doesn't really matter. Okay, so here we are. Oh, by the way, from last time I realized I told you these bolt pretensions around the holes, but you actually have to select like the bolt shank here. So that's one thing that I adjusted. So now this imported load, if you right click on it, you can go insert pressure, and that's the pressure from the CFD we just ran. So basically the pressure goes on everything that's exposed to the free stream. And the easiest way to do this, I find, is just go box select the whole thing, switch back to the single select, and so unselect all these bottom faces and these bolts that go into the fuselage, because they will not see any pressure. Okay, I think I deselected everything. So now geometry, click on that, hit apply. Now all those faces. And if you hit import load, oh, that's not good. Okay, I have no idea why it's doing that. It ran fine yesterday with the same file. I'll just delete this and see if I can. Also, if you don't know, if you control click on something that's green, then you can get deselect it while still having everything else selected. That's all I'm doing. I will not run that, but I will, or I'll try to run the FEA and we'll see what happens, hopefully. So basically, you want to insert some plots to actually get stuff out of this. So go insert stress. And you most of the time pick this von Mises. Basically, it's failure analysis under, was it ductile? Yeah, ductile failure. So that's what you'd see in like aluminum. That's kind of the most common. Like the other ones are, these are all various failure mechanisms, but von Mises is pretty common. Also, because we're interested in how the fin's going to deform, I usually insert total deformation. So if we hit solve, we'll see. Okay, yeah, I don't know why it's not importing that pressure, but I will open up the other file I have. Okay, so here's the one that actually worked. Let's say we did the same thing, imported pressure, and it actually did import everything. So the max pressure is, and this is gauge pressure, I believe, is about, it's like 0.1 megapascals. You get equivalent stress. You get this plot, so it makes sense the highest stress is kind of at the base here. kind of want to hide this foot, but I don't know where the thing is. So right, because the whole thing's kind of bending, so it makes sense that this edge that is like most fixed has the highest stress. And there's pretty low stress on the foot. This is why I think this simulation is kind of weird, because these bolts are moving so much less than this whole assembly. So something needs to be investigated. I think part of it might be the bolts are getting high pressure zones. And there's also strain. And that's basically the whole thing. So usually you have to run it more than once because you have to adjust stuff and the geometry changes, but that's the gist of it. I hope that kind of made sense. Also, you can see this max stress, like not even a megapascal, so well, carbon fiber can obviously handle that. You can also use this probe tool if you want to see exactly the stress at any given point. Oh, there's also this scale. We'll scale the deformation if you want. And that is it. So like I said, this is not the be all end all. I'm just trying to work through the fin stuff with other people and hope that this is a good reference for future stuff. So